From the Library of Congress in Washington, D.C.
Good morning. I'm Michelle Cattery-Bradley, a reference specialist in the Science, Technology, and Business Division of the Library of Congress. Welcome to today's program on mapping water use from space, in which we'll learn about the measurement of water use via applications of space-based technologies. Today's program is the fourth in a series in 2012. Jointly sponsored by the Science, Technology, and Business Division and the NASA Goddard Space Flight Center. Access to fresh water is a daily issue of life or death in many parts of the world, and it means healthy crops wherever they are grown. Water is central to the economies of U.S. western states, where legal battles over fresh water have become common. Now that the means to objectively measure and map water use with observations from space-based satellites has been discovered, and as it moves from innovation to everyday operations, it can be used for practical water monitoring. Research scientists have learned to measure the exchange of water vapor between the land and the atmosphere, which is called evapotranspiration, ET. ET is made up of all the water that's evaporated from surfaces and all water used by plants in the process of photosynthesis. ET monitoring lets us know how much water is left behind to do things like grow crops, provide drinking water, or feed the regional streams and river systems. The process of ET can now be monitored from space, making it an invaluable tool where Earth-based monitoring is either lacking or unavailable. It can help with monitoring drought, managing water, planning for irrigation, and predicting crop yield, all key areas for farming and natural resource management. Our speaker today is Dr. Martha C. Anderson. Dr. Anderson is a research physical scientist in the U.S. Department of Agriculture's Agricultural Research Service in the Hydrology and Remote Sensing Laboratory in Beltsville, Maryland. Her research interests focus on mapping water, energy, and carbon land surface fluxes at field to continental scales, using thermal remote sensing with applications in drought monitoring and soil moisture estimation. Dr. Anderson received a BA degree in physics from Carleton College, Northfield, Minnesota, and a PhD in astrophysics from the University of Minnesota, Minneapolis. Her interests in environmental issues have steered her towards research in Earth observation using satellite imaging systems. This has led to international collaborations in monitoring water resources around the world. She served as a member of the Landsat science team from 2006 to 2011. NASA has graciously provided literature and handouts on this research, which are in the lobby. There are also some related books from the Library of Congress collections that are on display, which we encourage you to look at. If you need more information, NASA's Jeannie Allen is also here to provide help. Today, please join me in welcoming Dr. Martha C. Anderson.
Well, thank you. Thank you for coming today. So, yes, I'm Martha Anderson, and I work for the USDA Ag Research Service, and I'm stationed in Beltsville, Maryland. I work in the Hydrology and Remote Sensing Lab, not too far from here. And today I am going to be talking about monitoring and mapping water use and water availability at scales from individual farm fields all the way up to the nation, continents, and up to the globe. We do this by looking at the Earth's land surface temperature. Very much like with the human body, temperature is a good diagnostic of how healthy the planet is and how much water it's cycling. And surface temperature is something we can measure fairly accurately from space. But to begin with, before I get into that, just a little background on me, why I'm here. I did my PhD actually in astrophysics, completely unrelated to what I do today. I studied acceleration of cosmic ray particles in galactic supernova remnants, University of Minnesota, and I used the Very Large Array of Radio Telescopes, which is down in New Mexico. I really like this. I like making maps like this. This is the Cass-A supernova remnant. But somewhere in the course of my graduate studies, it became pretty clear to me that I was much more interested in things that were kind of going on here on Earth than way up there. So through a series of events, I found my way into the field of Earth remote sensing, which is the study of using satellites to map out properties of the land surface and the ocean surface. And this turned out to be the perfect solution to my problems. It allowed me to look at environmental issues, but still use some of the observational skills I'd acquired in graduate school. You know, in a lot of ways, these two fields are kind of similar. You're just kind of observing things looking down instead of looking up. In both cases, it is just amazing how much we can learn about objects that are very far away from our sensing systems, purely based on their radiative properties. And that's what I hope to talk to you about today. So in my role at the USDA, I study the distribution and use of fresh water around the globe. And we know that water use, water security issues are going to become more and more important given the current trends in population growth and climate change. Of all the water that there is on the Earth, only 0.7% is available for human use. It's fresh water, it's not tied up in the ice caps. And of that little sliver of water, right here, about 70% of that available fresh water is used to support, agriculture. And that's why you have somebody from the USDA here talking to you about water use today. We know that these freshwater resources are not uniformly distributed over the globe. So this is a graphic showing the per capita availability of fresh water in the year 2000. And you can see there's some discrepancies in where the water is. The countries with the most per capita freshwater happen to be Suriname and Iceland, and those with the least, Egypt and the United Arab Emirates. Now, one kind of concerning aspect of this graphic is that some of these regions with low per capita freshwater availability also are areas that are undergoing some ongoing political unrest. So there have been international risk security assessments conducted with freshwater availability as being one of the key factors. This particular study made a ranking of countries in order of extreme water security risk. And as the report notes, some of these countries are already experiencing internal and cross-border tensions due to limited water resources, countries like Egypt and Sudan and Pakistan. We expect that these tensions are only going to become more acute as the climate continues to change and as some of these global water resources are starting to be unsustainably drained. Now, it is therefore, I believe, in our kind of national interest, both from a humanitarian standpoint, national security standpoint, to develop means for monitoring freshwater availability across the globe. We can't necessarily count on individual nations to give us a good accounting of their water use. Sometimes it's not in their best interest to give a good accounting of their water use. But more often than not, these data just are not available in any accurate form. And that is why our group in Beltsville and other groups internationally have been working on techniques for monitoring water use, or evapotranspiration, as we call it in the field, using Earth-observing satellites, because these satellites give us kind of a objective view on our global resources that sometimes we can't obtain through any other means. So briefly, what I hope to cover in this talk is, first of all, what is this water use process we call evapotranspiration, or ET for short? How do we monitor ET, or water use, using satellites? I'll give you some examples of some real-life applications for satellite-based ET, and then we'll just wrap up with what are the future prospects for water resource monitoring using satellite data. First of all, evapotranspiration. What is this? This is a hydrology term. If you talk to a water resource manager, they may use a similar term consumptive water use. And this is a little movie that NASA put together to demonstrate the concept of evapotranspiration. I'll see if I can fire it up here. Okay, there should be a rain cloud appearing. There it is. It's coming over the land surface. It's raining on the land surface. Some of this moisture infiltrates into the soil, and some of that is taken up by the root systems of these plants, and that makes them happy. They were a little stressed. Some of the water is evaporating directly from the soil surface. Much of that water that's taken up by the plants escapes through tiny pores in the leaf surface in a metabolic process called transpiration. That's the crop water use component. So you have evaporation from the soil, transpiration from the plants, evapotranspiration. So it's the net exchange of water between the land surface and the atmosphere. We know that ET is a major component of the global water budget. About 60% of the water that's applied to the land surface in the form of precipitation is believed to be returned to the atmosphere through ET. So if we want to understand the global water budget, how it's changing in time, we have to find ways to monitor ET at large global spatial scales. But this ET data is also useful at much smaller spatial scales as well. If we wanted to know what the water use patterns were over the Central Valley of California, it might look a lot like this, if you can see that. This is a map made with the Landsat satellite. So what do we have here? These green patches are irrigated agricultural fields, and they're using a lot of water, typically quantified in terms of millimeters of water use per unit time, in this case a whole growing season. You can also see the background moisture availability or water use that would exist in this area if humans weren't in there irrigating. This kind of spatial information is very valuable to kind of a broad range of stakeholders. The growers clearly want to know how much water their crops are using. They want to know when they need to reapply water in the form of irrigation. Water resource managers need to know this information so they can plan the future water distribution infrastructure for the state of California. And I'll touch on some of these applications a little later in the talk, but first of all, how do we make maps like this? How do we map water use using satellite data? And as I mentioned before, the key is for most satellite-based ET retrieval algorithms, the key is the land surface temperature. I'm going to use a human analogy over and over again today. As with the human body, a cooler body or cooler land surface tends to indicate a healthier, better hydrated land surface. So essentially we're making these maps using different size thermometers flying around on satellite platforms. You may have some familiarity with thermal imaging if you've ever had a home energy audit. Has anybody had a home energy audit before? We have, I know we have. They may give you a picture like this of your house, showing you all the leaky windows that you need to replace because they're too hot, and this guy has got some kind of issue with his insulation in his attic. He's losing a lot of heat through his attic. Using thermal sensors that operate in these thermal wave bands, which are much longer than our eyes can detect, we can remotely determine the physical temperature of an object purely based on its thermal radiation properties. So if we use those same kind of thermal imaging sensors to look at a vegetated land surface, you may see some pretty strong temperature contrast. Healthy green vegetation tends to be much cooler than the soil background, as you can see here. Now, why is this? It's because of evaporative cooling. This looks like it was a pretty dry field at this time. It's very sunny. The soil surface is dried out. It's not evaporating a lot of water right now, and it's achieving some pretty high temperatures. These yellow tones you can see here, that's like 50 degrees Celsius, 120 degrees Fahrenheit. In contrast, the corn plants have these rooting systems that they can use to mine water from deeper in the soil profile. So they can continue to transpire water long after that surface layer has stopped evaporating. As with sweat, the transpiration helps to keep the plants cool. So in some sense, the temperature of the soil and the vegetation components of this scene is giving us a good clue as to how much water is being used by each component. and we can get a quantitative estimate of that water use or that water loss if we run these thermal images through a modeling system that computes the surface energy balance. And this is the one piece of science I'm going to show here. It won't be very long. If we know how much energy is delivered to the land surface from the sun and from the atmosphere minus the back radiation off the land surface, we can use surface energy balance to compute how much transpiration and evaporation must be going on to keep the soil and the canopy, the vegetation, at the temperature that we observe from the thermal imaging satellite. Surface energy balance, conservation of energy. They're fairly simple models. Now there are a number of satellites currently in orbit that are giving us this thermal imagery that we need to run these surface energy balance algorithms. And I'm listing here a couple of these instruments that we tend to use in our work, and I've ordered them in order of the spatial detail that these sensors provide. From very coarse scale sensors like GOES, which can really only see or distinguish features on the landscape that are very big, like 5-10 kilometers large, several miles in dimension, down to much finer scale sensors like the Landsat satellite that can see features as small as like a football field. Now it so happens, unfortunately, due to instrumental constraints, data collection rates, and so forth, that as spatial resolution of these sensors increases, the temporal resolution tends to decrease, the rate at which it can acquire imagery. And that's too bad for water resources. We'd really like to have a sensor that saw things at 100 meter spatial resolution and gave us a map every 15 minutes, but such a sensor doesn't exist right now. So we have to make creative use of all the different types of sensors we have available to us. At the coarse end of the spectrum here, we have these geostationary satellites, and these are run in the United States by NOAA, and they're used mostly for weather forecasting. The geostationary satellites orbit the Earth at the same speed that the Earth rotates. So it's always getting the same hemispherical view of the land surface. And that's really very useful because we can acquire images really rapidly in that kind of configuration. We can kind of make a movie of how ET is changing over the continent during the course of the day. But because the field of view of the sensor is so wide, it's not giving us a lot of spatial detail on the ground. At any given time, there are typically 2 GOES satellites operating over the U.S. We've got GOES West giving us a view of conditions over the Pacific Ocean, and GOES East that's looking at the land surface and the Atlantic Ocean. We typically stitch together ET maps developed from each of these sensors to give us fairly decent coverage over both the North and South American continents. At the other end of this spatial resolution scale, we have the polar orbiting satellites like MODIS and Landsat. And these satellites give us a lot finer spatial detail, but the temporal frequency isn't so good. They give us a snapshot of conditions, maybe once per day or once per every couple of weeks. And this is a little movie showing the image acquisition strategy of the Landsat satellite. It's in a sun-synchronous polar orbit. So it's passing over the same patch of land at about the same time of day every time that orbit repeats over that patch. And that's very useful for modeling purposes. It's got a really narrow swath. It's going to take this satellite a long time to image the whole planet. But you can see the amount of spatial detail it's collecting within that narrow swath. So here we go. It's showing us how much coverage a single Landsat acquires during the course of a single day. It's going to take 16 days for this satellite to cover the whole Earth. It's building up successive orbital swaths. If we have 2 Landsats in orbit at the same time, in staggered orbits, we can get an image every 8 days, and that's quite valuable. And we had that for a while when Landsats 5 and 7 were both fully functional. Now the MODIS satellite, very similar. It's in a polar orbit, sun-synchronous, but its swath is much wider than Landsat. So it can actually cover the whole Earth's surface about once per day, but the spatial detail is not as fine as Landsat. We can make these maps of evapotranspiration using any of these thermal imaging sensors that I've discussed. And if we kind of stack them up in order of scale, one might envision in the future a kind of a Google Earth for water resource monitoring, where you can zoom in and look in great detail at the distribution of moisture availability in regions of specific interest. Here at the continental scale, this is a map stitched together from GOES east and west. And you're seeing the strong east-west gradient across the United States in precipitation and vegetation cover amount. We have much more rainfall, much denser vegetation in the eastern U.S., leading to these higher ET rates, or water use rates, indicated by the greener tones. And these areas happen also to be cooler than the west. If we zoom in a little closer using this MODIS polar orbiting satellite, start to see some hydrologic features emerging in the landscape. You can see there, if you look closely, there's some enhanced ET along these major riverways here. Zooming in even further, looking at Landsat, Landsat has the unique ability to differentiate water use on a field-to-field basis. That is incredibly useful for agricultural applications, and that kind of detail is lost with the coarser resolution sensors. We can also make maps of how water use is distributed within a given field if we have very high resolution thermal imaging, maybe collected by an aircraft. And that was the case here, where we're looking at a cornfield growing next to a soybean field. The corn is using a lot more water at this point in the growing season. You can also see there's kind of a strange, if I can get my mouse back here, this linear feature that's running through this area. This was an old railroad bed that used to run through Ames, Iowa, and it was removed a long time ago, but the soils are still compacted locally around that railroad bed, and the crops don't grow very well there. So you have a local reduction in T, the transpiration component of ET, and we can see that very clearly in the thermal imagery and in these retrieved ET maps. So you can get a lot of spatial detail if you go fine enough. There is use for ET information at all these different spatial scales. All these thermal images are very useful to us. At the continental scale, moisture patterns, exchange of water vapor between the land and the atmosphere is really important in determining the regional weather patterns. So NOAA is interested in ET information at this kind of spatial scale. At the state or basin scale, water resource managers like this kind of information. They need it to run their hydrologic models and do their regional water use assessments. At the Landsat scale, there's just a host of applications monitoring water use at the scale that it's actually being used. This is a zoom in on a part of Orlando. It's around the Disney World region, actually. You might recognize this. This is the Seven Seas Lagoon, where all the resorts are, and Disney World is Magic Kingdom's right over here. And this is the big parking and transportation center. You leave your car there, you get on the monorail. We can see it's very hot, very dry. It's a paved surface, not a lot of ET there. There's another interesting set of landscape features over here to the west. These happen to be rapid infiltration basins that are used to dispose of the treated wastewater that's coming off the Magic Kingdom. Now, they're used periodically when there's an overflow. They don't appear to be in use at this late time in the tourist season because they are also very hot and dry. This is the level of detailed water information you can get at the Landsat scale. Landsat has a long history of collecting imagery around the world. The first Landsat was launched back in 1972, Landsat 1. And I remember reading about this in my parents had National Geographic. I remember seeing this article, like, how cool are these images that they're making of the Earth these days? The first thermal imager was added to Landsat 4 back in the early 80s. So right now we have 30 years worth of near global water use information, unmatched by any other water use data archive available. With this Landsat thermal image archive, we can study how water use patterns have changed around the globe over the past 3 decades as these urban areas have expanded and as forests have been converted into agricultural land use and sometimes into subdivisions. Even though Landsat gives us a snapshot only once every 16 days, an instantaneous snapshot, every 16 days or maybe longer, depending on cloud cover conditions, scientists have figured out ways to interpolate water use between those overpasses so we can get time continuous water use information. For example, in our lab, we've been working on a technique for fusing information from multiple different thermal imaging systems. And this is work that's been done by several people in this room, and I thank you for coming. We use the GOES data, the geostationary data, to derive the daily curve in the evaporative flux to get the daytime total flux. MODIS gives us a little bit higher spatial resolution, snapshot once per day. But it's the Landsat satellite that really brings us down to water use features that are recognizable on the land surface. Well, what this algorithm does is it pairs MODIS Landsat image pairs on days when they're available, and then it uses that spatial information to disaggregate the MODIS images on all the intervening days. So we end up with a time continuous mapping of water use at these various spatial scales. So what can we do with all this data? We can collect all this water use data. What are the applications? I'll give you some examples in the areas of water management in the western US, in monitoring drought and crop condition, and then also some more international applications in areas of food and water security. But first to the western US. There are several states in the western US that are actively using Landsat ET to inform better water management decision making right now. Many of these states are depleting their water resources at unsustainable rates, primarily to support irrigated agriculture. They need to have information on their water use. And some of the examples I'll show in this section were generated by Rick Allen, who's a researcher at the University of Idaho. He's done this in direct support of operational needs by the Idaho Department of Water Resources. As my friend Tony Morse, who used to work with the IDWR, likes to say, we can't manage what we can't measure. And Landsat gives us the opportunity to measure water use at the scale that it's being used. Here's an example of this. This is a map over the part of the Snake River Plain in central Idaho. And each of these black boxes here, these polygons, are associated with a water right. The maximum amount of water that right holder is allowed to extract from the community groundwater pool. And then all these little blue dots are groundwater wells that are extracting the water to use for irrigation or maybe other purposes. The IDWR's job is to figure out whether these rights holders are complying with their rights. Clearly they can't use more water than they are allowed to, but also according to Western water law, it's kind of a use it or lose it situation. So if the water is not being put to beneficial use, that right can become under jeopardy. So this is a clear example of the need for both historical and current water use information at the scale of individual fields. And this is a job that is uniquely well suited for the Landsat Thermal Image Archive. In the past, how IDWR used to do this is one technique was to look at electric power meter records. Essentially, they'd associate the electricity used by that pump to individual pumps to an estimate of the total volume of water that was pumped over some period of time. Oh, great! Thank you. Security. Cancel. All right. This was a really costly way of doing this. It involved a lot of on-the-ground work, often going around, visiting different sites, reading their power meters, and it was also giving some fairly low accuracy estimates. You could get some crazy seasonal water use estimates through this technique, kind of well outside the range of what one might expect from some normal cropping systems. But in contrast, they found that Landsat ET could be processed very cheaply, relatively cheaply. The USGS is distributing the Landsat imagery free of charge, so it's mostly just labor costs and interpreting the imagery. They also found that it provided much higher accuracy. The seasonal water use estimates were pretty well constrained within the limits of what one might expect for these different crops, and then you can just go and target some of these outliers who seem to be using too much. Idaho, other Western states are also using Landsat ET data for other applications, for resolving water rights disputes, for deciding what to do in the case of groundwater call. They're using it to negotiate and monitor interstate water compacts, a lot of applications that Landsat is currently being used for. Why do we need Landsat for this? Because this is not going to hold up in a court of law. There is no way to associate water use with an individual water user at this kind of spatial scale. But we can do that at the Landsat scale. The scale is very critical for these applications. And Landsat is currently the only satellite providing thermal imagery routinely at this spatial resolution. So Landsat ET, not just useful for water administrators, also can be very useful for the growers as well. They can use these maps to kind of track out how much water their different fields on their land holdings are used. Maybe use it to schedule irrigation. When do different fields need to be irrigated? Particularly critical in crop growing regions in semi-arid parts of the United States. And this is an example. This is the ARS field, facility in the Texas Panhandle outside of Amarillo, Texas. The Ogallala Aquifer, which feeds the groundwater for this region, is declining very rapidly due to over-extraction for irrigated agriculture. They have to use their water very sparingly and very wisely. They need information on how to do this. I've made a little map here or a movie actually, of daily ET over this agricultural area that I'll show you. You will see a couple fields. This is a unirrigated cotton field in the foreground of this picture, grown side by side with an irrigated cotton field for experimental purposes, and you'll see these showing up in the movie. So I'll try to launch this. Here we go. To begin with, you're going to see some strong pulsing between dry and wet and dry and wet, and this is mostly due to differences in cloud cover. Clear days with a lot of ET, cloudy days with lesser ET. But you're also going to see some shifts in the management going on as well. This southern part of this pivot just turned on. You're going to see this southern part turn on too. This is a big concentrated animal feeding operation, and in the center is a huge manure lagoon. It's evaporating a lot of water. This is a residential area of Bushland, Texas, and the residents are likely irrigating or watering their lawns. This is this irrigated cotton field next to the unirrigated cotton field. And you can see the great difference in the cumulative water consumption by these two different management techniques. But I'll tell you, this unirrigated field did not do well in this particular season. The plants were stunted, it was very patchy. Irrigation is critical to getting a good crop in these climates, but the water has to be used as wisely as possible. Now, our group in Beltsville has recently started up a collaboration with some research scientists at the Ernest and Julio Gallo Winery in California. And these guys are also very interested in Landsat ET for managing their irrigation scheduling. But in this case, the issues of subtle differences in water use from field to field and crop stress is much more important than it might be for a corn grower in Iowa or Nebraska. We know that the best wine grapes are grown when the plants are under some degree of water stress, but not extreme water stress. So they're very, very carefully applying deficit irrigation techniques in this region. Very difficult to manage over the 200,000 acres that these guys have to manage. And that is why they are so interested in these satellite ET retrieval techniques. Especially at the Landsat scale, they can see the differential water use from field to field, which may be due to differences in the soil type, maybe it's due to differences in the kind of grapes that they're growing. Even row direction can influence the water use. Hill slope, microclimate, these are the types of features that we can capture through these satellite-derived ET maps. Final example, in the western U.S., we'd have to be not only worried or concerned about water use by agriculture, but also water use by natural species as well. In this case, it's an invasive species. And this is a map of water use over the Rio Grande River Basin south of Albuquerque. And a lot of this is irrigated agriculture out here, but right along the riverbed, that is consumptive use by riparian vegetation, mostly cotton, woods, and willows, and more recently, the salt cedar or the tamarisk. Now, tamarisk salt cedar was introduced into North America as a hardy ornamental, but it didn't have any natural predators. It started to spread, and early estimates of water use by salt cedar were kind of alarming. They appeared to be just giant water hogs, and people got concerned that they're going to suck all the water out of the river systems. So there was this campaign of massive salt cedar eradication that was mounted in some regions, including the release of a beetle that is known to defoliate salt cedar. So this program's been going on for several years. There has not been a significant demonstrated reduction in consumptive water use after this program has gone on. It turns out that the early estimates of water use by tamarisk were probably way too high. And this beetle is now spread to other riparian basins. It's causing some environmental damage. We really need to have better information about water use at the scale of individual land use patches. And again, critical for Landsat to be able to resolve that riparian vegetation from the surrounding landscape. Okay, going to shift gears just a little bit. We've got these time sequences of maps of water use, or ET. We can start to mine these data cubes in space and time, try to identify places and times where the water use was anomalously low, indicating drought. These ET maps can also serve as a kind of a unique and very valuable drought monitoring technique and crop condition monitoring technique. You may have seen maps like this before. This is the U.S. Drought Monitor, and it's the major record of drought events over the United States. It's updated every week, and if you want to see what the latest conditions are, you can look at this URL, or drought.gov. The Drought Monitor is being used extensively for many, many different types of applications, and many of these applications are not commensurate with the spatial scale of the data that's provided in this monitor. Those contours are very coarse, but they're being used to determine how compensation is distributed, due to yield loss at the end of the year. The Risk Management Agency, which is the arm of the USDA that operates the federal crop insurance program, is always looking for higher and higher spatial resolution drought information so that they can verify that these payments, these insurance payments, are going to the people who are really impacted. And this is another area where I think satellite-derived ET can play a major role. In our group, we've developed a ET-based drought index. And this is showing a map made with these GOES satellites. The red areas are areas of anomalously low water use, or ET. And indeed, the southeast of the U.S. was experiencing an exceptional drought during 2007. And this is a picture of Lake Lanier, which is the major reservoir supplying water to the city of Atlanta. By October of 2007, that reservoir was down to a 3-month supply of water for Atlanta, and people were really starting to panic. There were also threats of water war outbreaks between the states of Georgia and Alabama and Florida over some disputes about water allocations and some shared river basins. Things were kind of bad in 2007 in the southeast. The satellite-derived ET map gives us much higher spatial resolution information about how that drought was distributed than some of the standard drought indicators that are currently used to create these drought monitor reports. So over here, this is a map of soil moisture anomalies that were computed based on ground-based measurements of rainfall from the Doppler radar and from the ground-based rain gauge network. The reliance on ground data, which has been kind of the standard so far, has limited the resolution of these drought mapping products. With the satellites, we're not constrained by the ground measurements. We can get much higher spatial detail. It's reproducing those patterns in the rainfall deficits pretty well, but we're not using the precip data. That also makes these maps much more portable to other parts of the world where there aren't, Doppler radars every couple hundred kilometers. Here's another satellite-derived drought index. This is soil moisture data retrieved using microwave remote sensing, which is even longer wavelengths than the thermal band. And you can see that in that wavelength, the drought signal is completely lost in 2007. And this is because this is an area of very dense vegetation. There's a lot of forest cover down there. The water contained in the forest canopy absorbs the microwaves. This is why your microwave oven works. Water absorbs microwaves. So the signal is being lost in this dense vegetative canopy in the microwave wavelengths, but we're seeing it really strongly in the thermal wave bands. We're getting a different picture depending on what wavelength we look at. This is because, the crops are stressed, the forest is stressed. They're shutting down their transpiration. The reduced evaporative cooling due to transpiration is causing the leaf temperatures to elevate, and we're detecting that elevated temperature signal using our thermal sensors. So we're working with the colleagues at NOAA to put out these ET-based drought maps in real time. We have a web-based delivery system that will be going live within a month or so. We hope to expand this very quickly to include all of North America and Central America as well. We're also working on techniques to combine this kind of coarser scale information that we get from the geostationary satellites about drought with finer scale data from some of these polar orbiting systems like MODIS and Landsat to try to get down to stress conditions at a farm-to-farm level. And here's another example where we can resolve riparian ET from the background. That's the kind of information that's really needed right now by the action agencies. Now, all these types of monitoring techniques that I've been talking about, we've tested them very well over the United States, can be applied globally wherever we have this thermal imagery. And in fact, it probably has more value in some of these other countries where they don't have the dense ground-based monitoring infrastructure that we have here in the US. We've recently ported all these tools to Europe and Africa using geostationary satellites that are operated by the Europeans. The Meteosat satellite, operational satellite, sits at 0 degrees longitude over the equator, and it gives us a really nice full face-on view of the African continent. One of the projects we're working on is to use these Meteosat land surface products, again, mostly land surface temperature, you can see a little movie here, to do a kind of detailed water balance analysis over the Nile River basin. And this is a very interesting case. It's a trans-border large river basin where multiple countries are dependent on water coming out of the same source. You've got the White Nile that's originating in the Equatorial Lakes region. You have the Blue Nile that's draining much of the Ethiopian highlands and feeding into the main stem Nile. But all along the course of these different segments of the Nile, water is being diverted to support irrigated agriculture, and we need to know how much water is being diverted to do the water budget analyses. For example, in the Nile Delta, where the Nile in Egypt runs into the Mediterranean Sea, there's a gigantic irrigated zone there where they're using a lot of the water. Also in Sudan, there's a big irrigated area, the Gezira scheme. You can see in detail using Landsat, you can see these intricate, elongated network of fields that have developed along these irrigation canals. We need to be able to quantify this water use, this diversion. Water use by upstream countries is going to affect the water supply to the downstream countries. So really, the only objective source of information about what's going where may be coming from these satellite products. This is a map of seasonal water use over the Nile Basin. And this is this index that we use in the drought monitoring. And in both cases, you can see there is, again, a strong gradient in moisture conditions as you move from the Sahel, the grasslands of the Sahel, up into the Sahara Desert. You can also see the additional rainfall that the Ethiopian highlands receive relative to surrounding areas. A couple other features of note, again, the enhanced ET we see over the Nile River Delta. It's also a big wetland in the White Nile called the Sud, and it's a major sink of water along the Nile. Very important to quantify how much water is being lost there. Difficult to do, but I think these satellite tools are going to give us a means for estimating water loss there. So here's just a quick movie on changing water use patterns over this Nile. Whoop. There we go. Water, this Nile Delta. You see as the rains come, this wave of green vegetation moves northward, and the highlands of Ethiopia are greening up, and then it all recedes in the fall as the rains go away. You can also see cycles of water use in the Nile Delta related to the cropping cycles and the supply of water from the Nile. Very useful information, temporal and spatial. We've applied our drought monitoring tools over this region, and we see a very clear hotspot in anomalously low water use, water availability, coinciding with the hotspot of the famine in Somalia and the Horn of Africa in 2011. The hope is that with the increased spatial resolution that we can get from these satellite products and the timeliness, because we can create these products almost, that night for the previous day, this may help in the future to better target relief efforts, mobilize efforts earlier. We've been kind of driving some of these monitoring techniques in a case study over the Blue Nile Highlands, the Abai Highlands, and this is in collaboration with Ethiopian scientists and U.S. scientists in an effort to promote better climate resilience in some of the very vulnerable agroecosystems that exist in the Blue Nile Highlands. So they get a lot of rainfall there, but they're still, these rural subsistence farming communities are faced with a lot of challenges. The soils are highly erosive. You can see right here some of the critical erosion that's going on. There's also significant land use pressures causing them to farm on unsuitably steep hill slopes. And oftentimes, look at this, they're farming right up the edge of a gully. This is exacerbating the erosion problem. The erosion carries away the rich, good topsoil, and what's left behind has much lower water holding capacity. It makes these soils much more susceptible to flood and drought. So it's a big problem. Then all that sediment gets carried into the Blue Nile, which isn't very blue, gets transported downstream. It's silting up downstream dams and downstream nations, causing significant costs for dredging annually. Another aspect of transborder water management problems. So the goal of this case study is to try to develop a suite of information products that is really tailored to this Blue Nile Highlands area that might provide some information for better land management, better adaptation to changing climate conditions. If we have soils map and maps of hill slope or digital elevation models, along with kind of natural moisture availability maps, we can map out erosion potential. These types of maps can be then used by the communities to better plan their land use. Where should we grow crops? Where shouldn't we grow crops to minimize erosion? What diversity of crops may be best suited for different parts of the landscape that may be more resilient to the range in climate conditions that they're being subjected to now? And then we also have flood and drought monitoring capabilities with the satellites, hopefully at very, very high spatial resolution, allowing these communities to take some precautionary measures. So these communities are remote, but there are a lot of cell phones out there, and there's good political infrastructure, good peer networking, so there's a very good kind of route for this information to get disseminated to the actual farmers. It's a participatory project, so we're hoping that by engaging the communities, we have a better chance of making products that are relevant to their needs. And again, the spatial scale of the information is going to be critical. We need high spatial resolution to match the variability that they're seeing in the landscape and match the scale at which these decisions are being made. Again, that's the scale of the Landsat data. Okay, future prospects will wind up here. I've tried to make the case that satellite imaging is useful for monitoring water resources at different spatial scales. What are our prospects for water resource monitoring from space moving forward? Now, at the coarse spatial scale, I think the prospects are pretty good. There's geostationary coverage of most of the landmass around the globe. And these weather satellite programs tend to be relatively consistently funded. We always want to know what the weather is. We are developing global ET and drought monitoring products using this international suite of geostationary satellites, and we hope to have this automated and broadcast on the web in a routine fashion. On the other end of the spectrum, at the very fine scale end of the spectrum, with Landsat, our prospects are not quite as clear at present. We have the Landsat Data Continuity Mission, which is due to launch in January of 2013. And so that's the next Landsat, Landsat 8. And we're looking forward to that. We hope that all goes off as planned. We have a bit of a data gap right now. Landsat 5 and 7 both are kind of in a failure mode. So this growing season is a little touchy. We really want to get something back up there so we can start monitoring again. After LDCM, however, it's not clear at present what's happening with the Landsat program. There has been an ongoing effort to shift management of Landsat from NASA, which is more of a short-term mission, research mission agency, to USGS for longer-term operational management, with NASA still involved in the satellite development. But this transfer has not been going smoothly. It's kind of stalled out at present. And then we top this off with our budgetary issues. The funding for the Landsat program is going right down from a FY12 budget request of $48 million for development of the follow-on Landsats, of which $2 million was actually allocated, and that for studying kind of the range of alternatives to Landsat that might exist out there. And to FY13 with a request of only $250,000, again for just assessing Landsat alternatives. None of this bodes very well, given that the typical launch or window from funding to launch of a Landsat satellite is about 6 to 7 years. So even if the program for Landsat 9 was fully funded next year by some miracle, we're not going to get a launch until well into the 2020s. And this is well beyond the design life of LDCM. So we're looking at another potential extensive data gap. So there's some angst growing in the water resource monitoring community based on this uncertainty in the Landsat program. And this is a cartoon that was drawn by the son of a colleague of mine out in New Mexico. And so he's got, Earth is sick in bed, and he's saying, Dr. NASA, can you take my temperature? I'm feeling kind of sick. And Dr. NASA says, sure, I'll take your temperature with my Landsat, which is right here. And he says, okay, can you take my temperature? Well, maybe we'll take your temperature in 2020, maybe 2025. We'll see when we can get around to this. So I thought that was pretty good. Given the kind of broad array of water resource monitoring applications and other types of resource monitoring applications that have developed around this Landsat data archive, there is some urgency in finding this Landsat program a good home pretty quickly and starting work immediately on developing the follow-on Landsat so we can maintain this continuity of data collection that we've had over the past years. Again, I'll end with my message. We can't manage what we can't measure. With that, I'll stop, and if there's time for questions, I'd be glad to answer them.
Please, we'll just repeat the questions after they've asked so that they can be captured fully.
Absolutely.
And go ahead.
Okay, right here.
Yeah, you mentioned that I think Landsat 5 and 7 were kind of in failure mode, and Landsat 8 hasn't launched yet.
Yes.
What time period do we have data for the last, like 2007 to 2010 that's been coming in, or?
Yes. So it was kind of the end of, and Jeannie can correct me on the exact date, but it was the end of last year where Landsat 5 stopped collecting routine data, and they either have or will turn on another instrument, the MSS, right?
Yeah, but we hasten to say that Landsat 5 was designed for a 3-year lifetime and
Yeah.
it launched in 1984.
Yeah, it's done its
more than
time.
its
Yeah.
So
job,
if
but
you're interested in, say, California drought data from that 2007 2010 drought.
Yes. Landsat 5 was operating during that time. Landsat 7 is still operating, and it's been up there for a long time too, but it has an issue. It's got the scan line corrector issue where it collects full data in the center of its swath, but there are these little Venetian blind gaps off to the edges. So you just kind of have to hope that your site is in the center of the swath. And you can piece together information from Landsat 7, but it's not a very satisfactory mode of operation. So we,
And again, that one was launched in 1999 with a 5-year design
Yeah.
time. So
yeah, those instruments have really lasted. We cannot necessarily count on that for LDCM. That would be great, but we can't count on it.
What other inputs do you use for your model for determining evapotranspiration from land surface temperature?
Very good question. So the question is, what other information do we need to compute ET other than just land surface temperature? Anything that affects the exchange of water between the land and the atmosphere. And primary inputs are amount of vegetation, because that kind of determines the transpiration component of ET. We also need to know the solar radiation, how much, what the solar inputs. And we can also derive solar radiation very accurately using geostationary satellites. We need to know wind speed, because wind determines the turbulence, and the turbulence is what drives the eddies that bring the moisture off the land into the atmosphere. We need to know surface roughness. Rougher surfaces transfer water and heat more efficiently than smoother surfaces. So something like a map of vegetation height would be useful. Those are the major other inputs. The meteorological inputs we can derive with pretty good accuracy just from some kind of weather analyses frameworks. We don't need to necessarily have very detailed measurements of those properties. It's the land surface temperature we need with very high spatial resolution and good accuracy.
Are the details published in papers?
Absolutely, and I can direct you to some papers if you're interested. Very good. Any other questions? One more question right here.
What about taking into consideration in your model when you have natural disasters or storm events such as a volcanic eruption, you have volcanic debris in the atmosphere, which may change the outcome of some of these areas, or that you have in the drought area, you might have a windstorm that picks up a lot of the surface and brings that up into the atmosphere. That would potentially impact the results of your evapotranspiration rates.
That's absolutely right. So the question is, what if there are some natural disasters that are kind of bringing debris into the atmosphere that are kind of maybe the primary impact would be to reduce the solar radiation load on the land surface. So we would have to accurately know how to model those impacts on the solar radiation inputs. Whether we can do that accurately, there are models to do that, to monitor aerosols and volcanic ash and compensate in the radiative transfer models for those aspects. It's something we would really need to test. What are the impacts on our accuracy under those kind of very unique events? But I think the main impact would be on the solar radiation load. Back here.
And so the size of some of these subsistence farms elsewhere in the world are often much, much smaller than in the western United States, for example. How do you deal with that when you're looking at Landsat resolution?
That's a good question. So the question is, there are fields in other parts of the world that tend to be much smaller size than the fields we have in the United States, where are actually relatively large. So Landsat at 100 meters resolution is very adept at resolving many of our fields in the United States. It's going to be too coarse for a lot of the cropping systems in Europe and in these the Ethiopian highlands images that I showed you. We do have techniques for sharpening up the thermal imagery, and the person who's doing that in our lab is sitting in the second to the last row back there, Dr. Feng Gao. We can use the shortwave bands that are collected on the same instrument. So on Landsat, it's collecting thermal imagery at about 60 to 100 meters resolution, but the shortwave data are at 30 meters resolution. We can use that shortwave data, which is related more to vegetation amount and other factors, to sharpen up the thermal imagery to 30 meters. That gets us a little closer to the target scale we need. Ideally, we would have thermal sensors that had 10 meters resolution, and we're collecting daily all over the globe. This would be ideal. We have to do what we can. We're not going to resolve every water use feature that we want to. Right here.
You've talked about the design life of Landsat programs, but are there other alternatives that are being discussed with regard to completely private satellites and or relying on information from other nations? Are those being considered? Is that partly why this funding has dropped off, or?
So the question is, besides Landsat, are there other alternatives for collecting this high-resolution thermal imagery, including private companies running the satellites in other countries? So Landsat kind of went through a period of private operation, and it wasn't a good time, I don't think, in the history.
Well, that was, it was attempted. Landsat 6 was designed by a private company, and it was the only one in the series that failed to achieve orbit, as they say.
Yeah.
And there was a study done before Landsat 8, Landsat Data Continuity Mission, on whether or not private companies could manage this, and it was determined over a couple of years that no, they couldn't. So this is not an easy question for us to answer in the position we're in. But,
Right.
So
One of the issues is that, for a while the Landsat data were being, there was a fee for the Landsat data, and it was quite hefty. And in fact, it was too hefty for most researchers to do any research, a lot of detailed research. We certainly couldn't build up these dense time data cubes if we had to pay $6,000 for every scene we acquired. The research was not going to get done. The science was not going to get advanced under that mode of operation. Since USGS opened up the Landsat Data Archive, the research has just exploded, and all sorts of new phenomena have been detected, and new types of monitoring tools have developed. So from a researcher standpoint, I'm very happy to have this open access to the data. Whether another country will put up a satellite of the quality of Landsat, I mean, hopefully that would be one way to increase our temporal resolution. If we had Landsat and there was another country that flew another similar satellite in a different orbit, we could improve our data collection frequency. That would be ideal. I have not heard of Landsat type data in the near term from other countries. That would be freely available to us in the U.S. That's another issue. And would be consistent.
So do change over time.
Right.
Do private companies, does it exist though privately for fees for others?
So the question is, are thermal data available by fee through companies? And I think there's a bit of an industry developing in the western states, people with aircraft flying over fields and collecting thermal imagery, because the growers are recognizing the value of these data for managing their crops. It's really expensive for them. I think Gallo, has thought about this too, but it's really prohibitively expensive. So if we can develop some routine techniques at somewhat lower spatial resolution, but something that can be processed automatically as soon as the imagery come down, this could be a service that's kind of provided broadly over the whole western states. But yes, there are companies that are providing this data at very fine spatial resolution from airborne, yeah. And there may be some plans out there for some commercial thermal satellites as well.
I'm so sorry. I encourage you to come down and speak in person, but we're going to wrap up this session for today, and I want to again thank Dr. Anderson for being with us.
This has been a presentation of the Library of Congress. Visit us at loc.gov.